Alright, so last time we talked about Lewis structures, then we talked about formal charge, then we talked about geometry and determining whether there's a dipole. All of those steps lead up to our ability to identify intermolecular forces, which tells us a great deal about a lot of the physical properties substances have, and we're going to discuss that as we go through the lecture today. So if you expect to be able to identify the types of intermolecular forces a structure can have with neighboring molecules, which causes the molecules to group together as a liquid versus staying apart in the form of a gas, for example, you really have to be able to do all of the steps in the process. Unless I give you a Lewis structure already drawn out, if I just give you a formula, you really have to start by drawing the Lewis structure. Then you can check for noble gas configurations and formal charge to make sure it's as stable as it can be. Then you can look at the geometry. If you haven't correctly analyzed the geometry and you don't have a good picture of what the structure looks like three-dimensionally, you're probably not going to analyze the polarity, and you may not analyze the intermolecular forces correctly. So you really want to focus on drawing these things as accurately as possible three-dimensionally, and that's something we'll talk about in the days after today, help to guide you through that. But once you have the structure drawn relatively accurately in 3 dimensions, then you can look at which sides of the molecule are negative, which sides are positive. We talked about that last time. And then you can look at the types of intermolecular forces, right? So intermolecular forces are attractions between separate molecules. And sometimes there's confusion about what the word molecule means exactly. So I want to clarify that. A molecule is a grouping of atoms that are all connected through covalent bonds. So if I'm talking about intermolecular forces, I'm talking about forces between two different or more different molecules, not attractions between different parts of the same molecule, right? So any grouping of atoms where all the atoms are sharing electrons through covalent bonds is a single molecule. So no matter how many atoms I have, I can bond as many carbons as I want. I can put whatever other atoms I want there. Let's say I've got an oxygen here, so the other carbons would have hydrogen. It's just not drawing them in to save a little time. I can recognize in a structure like this that due to the electronegativity difference between carbon and oxygen, there will be a partial negative here as the electrons shift in that direction, bring their negative charge with them. Due to the electronegativity difference here, the electrons will shift toward oxygen, create a partial positive. So this is an attraction between two different atoms. It's not technically intermolecular though, because this hydrogen and this oxygen are all part of the same molecule, right? So just want to emphasize that. Any grouping of atoms where all the atoms are somehow connected through some network of covalent bonds are all part of the same molecule. So when we say intermolecular, we'd be talking about this molecule attracting to another separate version of the same molecule that are not covalently bonded to one another in any way, and they just happen to bounce close together and line up their areas of partial opposite charge. So inter means between separate molecules. This here, this attraction between this area of positive and negative is intra. It's within the molecule. It's between two different atoms of the same molecule. So you want to make sure you understand the difference between intramolecular versus intermolecular, between different structures. So when our structures are neutral, meaning there's no overall charge, if there's no overall charge, there's no ions, there's no full formal charge, that limits the possibilities for intermolecular attractions to these three possibilities. So if you recall from Gen Chem, if a structure does have an overall charge, maybe I've got something like this, and I've got enough valence electrons to complete this noble gas configuration. That would create a negative formal charge. So this is an ion. It can undergo some of these types of attractions, but it can also undergo ionic attractions. So if that were to attract to another fully charged particle, that would be an ionic bond. If it were to attract to like a water molecule, where the water molecule doesn't have a full formal positive charge, but it does have a partial positive due to the electronegativity difference, that would be an ion attracting a dipole. So if this fully charged molecule attracted the partial charge, call that an ion dipole attraction or full charge partial charge attraction. So you want to keep those in mind as well, even though they're not really focused on in this section of the textbook. But if all our molecules are neutral and they don't have any formal charges, we don't have to worry about any of these ionic, specifically ionic attractions. So let's talk about these one by one. This is a review from Gen Chem. Hopefully most of you are really pretty familiar with this already, but there's a lot of details involved, and many of those aren't present in your mind if you don't talk about them and practice with them frequently. So we'll try to fill in those gaps if there are any for you. So dipole-dipole is probably the simplest one. The most confusion students have with this one is the term. So there's a reason why the word dipole is repeated twice here, and that's because a single dipole, just the word dipole, refers to a single molecule. Just to give a simple example here, HCl. As we just described on the last slide, a molecule is defined as a grouping of atoms sharing electrons. So as long as the chlorine and hydrogen aren't sharing any electrons with any other atom, that's the whole molecule. And that's a dipole because there's an electronegativity difference there. It creates a negative end and a positive end when there's opposite charges on opposite ends. That's a dipole. So the term dipole-dipole, though, refers to intermolecular forces because you can't have a dipole-dipole with only one molecule. It needs something else to attract to it. So one molecule can be a dipole, but one single molecule can't be a dipole-dipole. A dipole-dipole forms between two molecules. They could be identical or they could be different structures. As long as both molecules have areas of opposite charge to line up and attract, the attraction between two different molecules is the dipole-dipole, assuming that both molecules attracting have a polarity with opposite charges on opposite ends. So here's another example. Here I have acetone. Acetone has this CO double bond, and as we were talking about last time, the pi electrons specifically aren't very tightly held to the nuclei because of the type of bonding molecular orbital they're in. They're easily pulled towards the oxygen, so they're not going to be totally moving to the oxygen necessarily, but they're going to be shifting in that direction, and that creates pretty large partial negatives and positives there. Every molecule is going to have that permanently. Now the cloud of electrons is still kind of sloshing around like a fluid kind of randomly, and it might slosh back in the other direction a little bit, decreasing the quantity of negative and positive that are present, or it might just kind of randomly slosh to the right hand side, increasing the amount of negative and positive and making the attraction even stronger. So every single molecule won't necessarily have the exact same attraction to all other molecules at the same time, but there's definitely a big electronegativity difference there. So for the most part, they'll always have a negative end and a positive end, and then that's a dipole. If I have another identical molecule or any other molecule with a negative end and a positive, that's also a dipole. And so when they line up their negative of one molecule with the positive of the other, that's a dipole-dipole. So pretty straightforward. As long as you can identify the molecule as polar and has opposite charges on opposite ends, it is a dipole, and it can line up and attract another dipole to make a dipole-dipole attraction. And this affects the boiling and melting points. Right, so we want to keep in mind what is melting. That's going from a solid to a liquid. Boiling is going from a liquid to a gas. So what has to happen to go from a solid to a liquid? Well, in the solid state, these molecules are typically organized, lined up in rows and columns so that their negatives are optimally positioned right next to the positives, maximizing the strength of those attractions. In order to melt that solid, You got to break some of these attractions so the molecules can start sliding around past one another. I don't have to break them all because they still remain closely grouped, but they're constantly breaking and forming these dipoles as individual molecules maybe move over somewhere else in the structure and attract to different molecules from the ones that was initially attracted to. So in the solid state, all the molecules are optimally lined up and attracting. I have to break some of those attractions to allow the molecules to slide around a little bit past one another to make a liquid. So the more charge there is, the stronger and the closer they can get, the stronger the attraction, and the more energy or higher temperature is going to be required to get them moving fast enough to break some of those attractions and cause the melting to occur. So it takes a higher temperature to melt a substance with stronger intermolecular forces. And likewise, when I go from a liquid to a solid, the difference between liquid and a gas, the difference between a liquid and a gas is, in a gas, all the individual molecules are separated and they're moving around fast enough that if they do collide, they just bounce off. So that means that I have to get it up to a high enough temperature, the liquid has to reach a high enough temperature for all the intermolecular attractions to break and for the individual molecules to act independently and not be able to effectively attract because they're moving around too quickly. And so the stronger the attraction, the higher the temperature necessary to get that liquid to convert into a gas and break the remaining intermolecular attractions that weren't broken when it went from a solid to a liquid. So you should definitely, these two properties especially are directly related to the strength of the intermolecular attraction. And dipoles are relatively strong. Obviously, it'd be stronger if I had a full negative charge or a full positive charge. The higher the quantity of charge, the stronger the attraction. These are pretty large quantities of charge, so acetone is a relatively polar structure. Now, if we look at the CH3 groups, these take up a fair amount of space, and these CH3 groups are not really polar regions. There's a slight amount of partial positive on these atoms, but not very much because their electronegativity difference is small. Obviously, the electronegativity difference between carbon and carbon is very, very small. So the amount of positive on these is minimal. So the strength of the intermolecular attractions is also limited by how closely the opposite charges can get. And if I have these areas of not much charge, because the electronegativity differences in the CH3 groups are minimal, that kind of blocks to an extent how close the area of negative on this oxygen can get to the area of positive in the center of the molecule. And so even though there's a large partial positive on the carbon, the attraction here is not as strong as it would be if that large partial positive were more exposed on the surface of the molecule rather than kind of embedded in the center, surrounded by less polar CH3 groups. Again, the blue, the darker the blue, the more positive, and the darker the red, the more negative. So we can use this example here to illustrate how important dipole-dipole is to the properties of melting point and boiling point we just discussed. So these two structures are very similar. They have almost the exact same shape due to the central carbon in both being sp2 hybridized. They have almost the exact same mass because the CH2 group has a mass of 14 and an oxygen has a mass of 16, so their masses are almost the same. The difference is there's virtually no electronegativity difference between these two carbons, but there's a huge electronegativity difference between the carbon and the oxygen. So the polarity of this bond, especially the pi electron shifting up, creates the large partial positive and negative we just talked about in the example of acetone. And so when another acetone molecule is close to it, I'll just draw it up here. And it has a partial positive, that can line up with the partial negative and attract. And so it takes a fairly high temperature to separate those molecules, especially for the boiling point, to separate them and get them all independent because of the fairly large quantities of charge involved in their attraction. Here, I can't even really draw partial positives and negatives because there aren't really any significant electronegativity differences to speak of, and that's why it takes much less energy to get the molecules to separate from one another. So there are London forces here, which we'll talk more detail about in a few slides. That's why there is at least some energy required to separate the particles, because they do attract through London forces, but they don't have permanent areas of partial positive and negative on opposite ends to attract like the acetone molecules do. So I don't need nearly as high a temperature as I do to separate the acetone molecules from one another. Okay, so that leads us to hydrogen bonding. Hydrogen bonding is a type of dipole-dipole attraction. So there's always some confusion among students when we're identifying hydrogen bonding. So I want to try to clarify. This right here, this right here is a covalent bond. Whenever atoms share electrons, they go into a bonding molecular orbital. That's a covalent bond. It could be a pi bond. In this case, it's a sigma bond. A covalent bond is not a hydrogen bond. I really, really wish that chemists had chosen a different term for hydrogen bonding, because the word bonding sounds like a covalent bond, and that makes it really confusing. But you have to remember that a hydrogen bond is not a covalent bond. A hydrogen bond is not an example of a pair of electrons shared between two atoms like a covalent bond is, where the electrons exist in a molecular orbital spread out over both nuclei. A hydrogen bond is like a dipole-dipole. It involves one atom with a partial positive attracting to another atom with, in this case, it's the lone pair of the atom that carries a partial negative. So it's very similar to the situation with the acetone we just saw over here. Really, the only difference is, in the case of the acetone, the large partial positive exists on a carbon in the center of the molecule, and as I was just saying, it's kind of blocked to an extent by these other atoms. So when a carbon carries a partial positive, it's not really able to bring that very close to the partial negative and form a very strong attraction there. And so we just call that a standard dipole-dipole. A hydrogen bond, however, is an especially strong type of dipole-dipole, not only because there are large quantities of partial positive and negative involved in the attraction, but also because the hydrogen can only form one bond, and that means it will always be on the surface of the structure, ready to get close to any area of partial negative. Right, so there are really 2 points about this that you want to remember. One is that you have large quantities of partial charge. Why is it there's such a large quantity of partial charge in a hydrogen bond? Well, the reason for that is because the hydrogen has to be sharing electrons in a covalent bond with an oxygen, nitrogen, or fluorine. It has to be one of those 3. To qualify this partial charge attraction as a hydrogen bond, I need to have large partial charges. And the only way that partial charges will be large is if the electronegativity difference is large, because that causes the electrons to shift a lot away from the hydrogen, exposing its nucleus, creating an area of large partial positive and an area of large partial negative. And only nitrogen, oxygen, and fluorine are electronegative enough to do that to the extent where the hydrogen carries enough of a partial positive to set it up for this type of attraction. So I could have a hydrogen attached to a carbon, and then maybe that carbon is bonded to something electronegative like a nitrogen. The nitrogen is pulling electrons away, creating a negative. The carbon's pulling electrons away, creating a positive. There'd also be a positive on the carbon because all the electrons up here are shifting away from it. So if that were to line up next to another molecule of the same type, I'd have a partial negative, partial positive attraction. Would that be a Would that be a hydrogen bond? Well, the answer is no, because the quantity of partial charge on this hydrogen is not very much. When it's sharing electrons with any atom other than oxygen, nitrogen, or fluorine, the electronegativity difference is usually minimal, and so I only get a very small quantity of partial positive there, which means the attraction is not very strong. So to make the attraction strong enough for it to qualify as a hydrogen bond, the hydrogen has to be sharing electrons with one of these highly electronegative atoms to create a large partial positive on it. Then it can attract to the large partial negative existing on oxygen, nitrogen, or fluorine from a neighboring molecule. So when we talk about this in general chemistry, I always talk about it as a hydrogen sandwich. Hydrogen has to be sandwiched between two different highly electronegative atoms, one that it's covalently bonded to that creates the electron shift that creates the large partial positive, and the other that has a large partial negative because it's also pulling electrons away from something that's very low in electronegativity, and that is what creates the large quantities of partial charge that are necessary for the attraction to be strong enough to qualify as a hydrogen bond. And the other part of that is the proximity of the charges. The charges have to get close together, and that really does require, for the most part, the elements to be on the surface of their respective molecules. So water is a small molecule, ammonia is a small molecule, but you could have a molecule with 20, 30 atoms, and some of the carbons and other atoms might be on the inner surface, or not surface, but on the inner core of that molecule, and they can't really reach out to a neighboring molecule and form an attraction. So the proximity of the charges is possible with hydrogen specifically because hydrogen is always a surface atom. It's always on the surface of the structure because it can only ever have one bond. And that's why hydrogen is special. And hydrogen bonds are special because their attractions are pretty strong relative to other dipole-dipole attractions. So as we were saying, the hydrogen has to share electrons. The sharing isn't the hydrogen bond itself, but the sharing of electrons creates the large partial positive on the hydrogen if it's sharing with one of these three atoms, and then that large partial positive on one atom will attract a large partial negative of another molecule. So it has to be a second molecule coming in. On average, a hydrogen bond is about 20 times weaker than a covalent bond. Right? Again, it's still only a partial charge attraction. It's not like a covalent bond where the electrons are in an orbital attracting to multiple nuclei, and that really is a stable bond. It requires a lot more energy, about 20 times more energy to break that than to break the hydrogen bond. But covalent bonds we think of as pretty strong, so even though it's 20 times weaker than that, it's still a relatively strong attraction. Typically at room temperature, those attractions are often breaking and then reforming because they're not nearly as strong as covalent bonds. And that introduces a new term that we use called, it's a term called protic, and that basically means that there's at least one hydrogen in the molecule capable of forming a hydrogen bond. So in this structure here, it's protic specifically because of this proton. Right? A hydrogen is a proton. A hydrogen has really pretty much only a proton in its nucleus. Most hydrogen atoms don't have any neutrons. And the only electron they have is always shared with the other atom. So if these electrons get pulled away due to the electronegativity difference, it's basically just a proton being exposed. So when the proton is severely exposed because either an oxygen, nitrogen, or fluorine is pulling the electrons away from it, that we consider to be a protic substance because of the exposure of that proton, and the large partial positive that exists on it sets it up for attraction, strong hydrogen bonding type attraction. These hydrogens over here are not really protic sites because they're sharing electrons with carbon. The electronegativity difference is minimal. They only carry a slight partial positive, so if it wasn't for this hydrogen here, this molecule would not be considered to be a protic molecule. So here are some other examples to help illustrate the concept of something being protic. So we've got acetic acid here. Is this structure protic? How can we tell? Well, specifically, we're looking for a hydrogen that's bonded to an oxygen, nitrogen, or fluorine. And that's what we have right here. So the bond isn't shown there, but there's a covalent bond here. The electrons are pulled toward the oxygen, and so that exposes a large partial positive. And then that large partial positive can attract to the large partial negative of an oxygen on a neighboring molecule. That attraction is the hydrogen bond, and so that means this is a protic site and that this is a protic molecule. None of the other structures here are protic. What the other three here have in common is in each hydrogen, in each structure, it's always bonded to carbon. As long as my hydrogens are bonded to carbon, and most organic molecules have lots of different hydrogens bonded to carbon, as long as they're only bonded to carbon, it will never be a protic structure. I need a hydrogen bonded to an oxygen, nitrogen, or fluorine to give the hydrogen a large enough partial positive to attract to a neighboring molecule through a hydrogen bond and to be protic. Later, when we talk about substitution reactions later in the semester, about halfway through roughly, we'll see how protic solvents affect the way that the electrons move in the reaction and the outcome of the reaction. So this topic will come up again later in the semester, and we'll definitely review it again at that time a little bit. So here I've got two protic molecules where hydrogens are bonded to nitrogen, and one that's aprotic, meaning it's not protic. So aprotic means not protic. Protic means that there's a proton with a large partial positive that's set up for hydrogen bonding. Right, so again, if I just draw one molecule here, like this structure in the middle, just drawing one molecule, it's not capable of hydrogen bonding. If I say it's capable of hydrogen bonding, there's the implication that that would require another molecule to be nearby. So if another molecule came in, and the large partial negative on the nitrogen of one molecule through its lone pair formed an attraction to the large partial positive of this hydrogen's nucleus, that is the hydrogen bond. This structure over here can't hydrogen bond with another identical molecule because it doesn't, all the hydrogens are bonded to carbon. It's aprotic. All these hydrogens have very small partial positives. The nitrogen has a large partial negative, so it could hydrogen bond to a protic structure, but since it itself is not protic, it can't hydrogen bond to an identical structure. So like for example, if I have a water molecule, because this hydrogen is covalently bonded to oxygen, it will have a large partial positive, and that could form an attraction to the lone pair of the nitrogen. So it's not that this molecule is completely incapable of ever forming a hydrogen bond. It's just that it can't hydrogen bond to an identical unit of the same type of molecule. And that affects their boiling points. Right? So if I'm looking at boiling point, I'm talking about the pure substance evaporating. So that would be a situation where there's no water. I just wanted to point out what would happen if water were around. So if there's no other solvent around and all the chemical units look just like this, well, there is a dipole because the nitrogen does have a tetrahedral geometry. So the three CH3 groups are down here kind of at the base of a pyramid because of the trigonal pyramidal shape. So there is a partial positive in between those CH3 groups and a partial negative up here. And so it could line up next to a neighboring molecule, and the partial negative of one could attract the partial positive of the other. But it's only a mildly strong attraction. What's the reason for that? Well, there's really two reasons. One, the carbon-nitrogen electronegativity difference is not that big, so the quantity of positive here is not as big as the quantity of positive on a hydrogen. The nitrogen-hydrogen electronegativity difference is bigger. Oops. And 2, the partial positive here is really on the carbon. And the carbon has these hydrogens sticking off of it, kind of blocking it from getting close to the neighboring molecule's partial negative. So anytime your partial positive resides on a carbon, it's not going to be easy for that to get as close to an area of partial negative on a neighboring molecule, because there's other things bonded to the carbon that kind of get in the way usually. And so the attraction there isn't that strong, and it only takes a few degrees above 0 for that to start boiling. Versus the other 2 that are capable of hydrogen bonding, and this one is capable of even more hydrogen bonding, because if this molecule has 3 areas of large partial positive, well, then a neighboring molecule could come in and attract at all 3 of those sites, forming a larger number of attractions. Means that more of those attractions would have to break to get the molecule to escape its neighbors and become a gas. So an even higher temperature or more motion is necessary to break the intermolecular attractions that one might have with its neighbors. Any questions about any of that? Hydrogen bonding is also responsible for the double helix in part that you find in DNA. Each of the base pairs in the DNA is going to, whatever that base pair structure is, just put a star here, it's going to hydrogen bond to the neighboring structure. So one of these strands wraps itself around the other because of all the hydrogen bonds holding the 2 strands together. And that's a lot of hydrogen bonds, so that's a pretty strong attraction. It takes a relatively high temperature to separate the strands of DNA. In a protein, you get a similar situation. In a protein, though, the hydrogen bonds are intramolecular versus them being intermolecular in DNA. Right? Because DNA is a double strand. And the DNA has 2 complementary strands. One strand wraps around the other, and there's the hydrogen bond attraction between part of one strand and part of another strand. In protein, there's something called an alpha helix. This is a common way for proteins to fold up. They fold up into these ribbon shapes, and the ribbons here allow for one area with a large partial positive on one part of the ribbon to attract to an area of large partial negative on another part of the same ribbon. And so this long chain of atoms wraps up into the shape and allows for multiple areas where the strand will attract to other parts of the same molecule. So this is one molecule, this is 2 molecules, the DNA is 2 molecules. The one molecule, one protein molecule, is going to form a lot of intramolecular hydrogen bonds. So a hydrogen bond could be an intermolecular attraction or an intramolecular attraction if the single molecule can wrap around on itself and line up these areas of large opposite partial charge. Alright, so that leads us to the third type of intermolecular attraction for neutral molecules, which is London forces. Mainly we focus on London forces in instances where a molecule is nonpolar. But London forces exist for any structure that has an electron cloud, so any electrons at all in the molecule will set it up for London forces. So how does this work? Well, nonpolar molecules can attract to one another. We know that for sure. Otherwise, they wouldn't be able to form solids and liquids. They would always be a gas, but that's not true. So even hydrogen molecules can form into a liquid or a solid if you cool them down enough. There's a small electron cloud around the hydrogen molecule, and then there's a small electron cloud around the neighboring hydrogen molecule. That electron cloud only contains 2 total electrons, and the hydrogens have the same electronegativity. So on average, the electrons that are shared evenly around both hydrogens. But for an instant, there might be a moment in time, since the electron is a cloud, and it behaves like a fluid that can slosh back and forth, there might be a moment where the electrons just randomly, suddenly shift to the other side. And if that happens, then the electron cloud will be distorted onto one side of the structure. And if there's more electrons over there for a moment, that side will be negative and the other side will be positive. Is that going to happen dramatically in this molecule? No, because there's only 2 total electrons. And so even if they shift a lot, it's not going to create that much extra negative on one side than the other. And there's no multiple layers of electrons. There's no core electrons interfering with the valence electrons. There's only 2 total electrons. And those 2 total electrons get real close to the nuclei. So they're held pretty tightly. They don't really slosh that much. It's like, how much sloshing is there in a glass of water if there's only a little bit of water in there? It's not going to slosh around a huge amount. Or if I'm just carrying a glass of water and there's not much in there, it's not going to splash out because it's not sloshing around that much. If I compare that to, well, let me just finish this thought. So once that occurs, another molecule nearby could feel these charges and its electron cloud would respond accordingly. So if there's a negative end of this structure, what's that going to do to the electron cloud of this structure? Negative charges repel. So the negative charge of this cloud is going to shift away a little bit to the other side. So if that shifts away, that would create a positive end and a negative end. And now we have opposite ends that can attract. So in London forces, if the molecule is nonpolar to begin with, it doesn't have partial charges on opposite ends. But it can create them temporarily, either by randomly shifting the electrons or by having the electrons shift in response to another molecule that has a charge nearby, so that they can then create opposite charges on opposite ends and attract. And that's what happens in hydrogen molecules. It allows them to come together in the form of liquids and solids. So if we were to compare that then to a structure like, for example, iodine, if I just looked at the Lewis structures, well, they look very similar. But iodine has electrons all the way out to the 5th energy level, I believe. Its valence level, I think, is the 5th level. So that means in iodine, there's all these core layers of electrons around each iodine. And it's the 5th level that actually extends over both atoms. So here's my 2 nuclei. So this outer shell of electrons is very weakly attracted to the positive. And so this is like holding a large fish tank of water and trying to walk up the stairs. If it's really full, the momentum of you moving back and forth is going to really slosh that water around. And this cloud of electrons will randomly be very easy to shift to one side, and that will create very large partial charges temporarily. And so another molecule of iodine can then form a pretty nice attraction to it. So normally we think of London forces as being quite weak. In the case of hydrogen, they're very weak because there's only 2 electrons. Those 2 electrons are held relatively tightly. They don't shift around very easily, so the temporary partial charges that form are very minimal. But in some instances, when I have lots of layers of electrons, or maybe if I have a really long chain of atoms, instead of thinking about the London forces forming across the whole structure at once, I might have this big cloud of electrons over this whole structure. There might be localized areas where the electrons shift. So maybe part of the electrons in this covalent bond maybe just kind of shift up and create some tiny little partial positives. And then maybe over here, the electrons shift in the other direction and create some tiny little partial charges. So if I have a long chain, even if I don't have a large electron cloud with lots of layers that can easily shift and create these large temporary partial charges, I might be able to form lots of tiny partial charges all around the surface, and then that can line up with another molecule and have lots of sites of weak attractions, which adds up to a fairly strong attraction between the structure. So London forces become especially relevant when you have lots of layers of electrons, so they can shift very readily to create large quantities of partial charge temporarily, or when you have complicated molecules with large electron clouds where shifting can occur locally in different areas to create lots of tiny little partial charges to attract the neighboring molecules with. So, and this occurs because the electrons are a fluid that can constantly be in motion and shift around within their molecular orbitals. So this is just kind of illustrating that. Here I've got 1, 2, 3, 4, 5 carbon chain, and we can see the cloud of the outside of its one of its molecular orbitals. So since the carbons are all have the same electronegativity, normally I would expect this molecule to be nonpolar. What this is showing here is a temporary shifting of the electrons to one side just because of random chance. So that is called, the term is not here, that's called an instantaneous dipole. Instantaneous meaning just for an instant, just by random chance, the electron cloud just shifts to one side. That creates negatives on one side and positive on the other side. If that happens and there's a neighboring molecule, as we said before, it will shift in response to the other one. And so that's called an induced dipole. So these are not permanent dipoles, they're not polar molecules. These are nonpolar molecules that have a temporary shifting of the electrons. One due to random chance, and the other because it was exposed to this one. So if this one creates a lot of negative on one side, that will cause the electron cloud on the other one to shift away from that due to the repulsion, and these small positives that are created can attract here, and that can allow the molecules to start sticking to one another and exist as a liquid rather than a gas. So pentane is actually a liquid at room temperature because of these London force attractions. It has a relatively low boiling point though, because they're not very strong, because they're only temporary. And so the charges only exist for a little while, so the attraction only exists for a little while, right? Why are these charges here? Well, because one molecule just randomly, the electron shifted to one side. So since that was random, maybe they'll shift back to being evenly distributed, or maybe they'll shift to the other side and create partial negatives on the other side and partial positives over here. And so that would cause these two molecules not to be attracted anymore. And so the attraction is kind of fleeting. And overall, it's not very strong. If I had a longer chain and I could create lots of partial charges all around, the attraction might be more significant. It would build up to a stronger overall attraction between the molecules. So even though they're weak, if I have a lot of them, they can add up to significant attractions between the molecules that have big impacts on the physical properties. And that's how some animals take advantage, like the gecko takes advantage of that by having lots of surface area on its feet, and that creates the surface area creates a lot of opportunity for these nonpolar molecules to to touch one another and have their temporary areas of partial charge cause them to form some decent attraction. Just to point out, if I did have a polar structure, like acetone, so as we said, the acetone has a permanent dipole because of the electronegativity difference here. Electrons naturally shift to this side away from the other side, but it's still a cloud, and it can still shift randomly. So sometimes it might randomly shift in the opposite direction a little bit. So I might have a smaller negative and positive created for a moment, and then the attractions won't be as strong. Or the electron cloud could randomly shift in this direction and make even larger quantities of negative and positive. So not every molecule is going to have the exact same degree of polarity because of that random shifting. But it is a factor. So the London forces created by this random shifting of the cloud does at moments increase the quantity of charge created, and that allows the structures to be attracted more strongly than they would be if London forces didn't exist. So if we only looked at the dipole-dipole attraction between molecules of acetone, we wouldn't predict them to be attracted as strongly as they are in real life, and that's because there is some contribution of the randomness of the London forces adding to how strongly they attract, because it's adding, at least in moments, to how much charge there is with which those molecules can attract to one another. So when it comes to London forces, we can use them to explain a lot of different properties. So as we were talking about boiling point, so here are 3 different structures: butane, pentane, hexane. The difference is the length of the chain, or the number of electrons, or the size of the electron cloud, right? So when the electron cloud is smaller versus cloud, in the larger electron cloud, there's just more electrons randomly shifting. The molecular orbitals extend over more atoms, and they can shift more readily to one side or the other. And if the cloud is large enough, there might be lots of small areas where they shift around, creating lots of little partial charges here and there that can allow another molecule to come in and form lots of attractions. So the more surface area there is on the outside of a neutral molecule, or a non-polar molecule I should say, the more surface area there is, the more opportunity there is for these small but significant partial charges that form temporarily to attract the molecules together. So because hexane is attracted to other hexane molecules through lots of little partial charges forming temporarily, it actually has a relatively high boiling point, especially compared to butane, which has a smaller surface area and will only have maybe a couple tiny partial charges forming at a time, and so the molecules aren't attracted nearly as strongly. And we can also confirm our idea about surface area if we look at structures like this. So here I've got 3 isomers of pentane. Each of these has 5 carbons, and each has 12 hydrogens. The difference is the couple on the right are branched, and the one on the left is a straight chain. And the branching makes more of like a spherical shape to the overall molecule. And so it's more compact, and there's less surface area. So here maybe the electrons can shift a little bit and create a couple small partial charges, but with less surface area, even if I put partial charges all the way around the surface, there are only a couple sites where this molecule can attract other molecules. So when the molecules are more elongated and out, there's more surface area, and so I can get a larger number of partial charges around the outside to attract this molecule to its neighbors. And so it takes more energy to separate them when they're more strongly attracted due to having more opportunities to attract with more surface area. So you want to keep in mind surface area is a significant factor that explains the differences in these boiling points, and it also is important when looking at how strongly molecules attract one another. Alright, so that leads us to the first quiz question, where you all last time identified the correct geometry. So we know this carbon is linear, and we know this carbon is tetrahedral. So if I wanted to draw out all the bonds so I can kind of see the polarity, mainly it's the carbon-nitrogen bond that we said creates a negative end and a positive end. Can this molecule hydrogen bond with a neighboring molecule that's identical to it? No, it cannot, because the main area of positive is on a carbon. So there is a permanent dipole here, and one molecule's negative can attract the other molecule's positive. So that's a dipole-dipole attraction. But the carbon is kind of blocked a little bit by the size of the CH3 group. It's hard to get that negative in there closely, so it's not that strong of an attraction. And also the hydrogens are all bonded to carbon, so they only have very small quantities of partial positive, and so they're not going to really be involved in the attraction very much. So the answer here is London forces. There's always London forces. The cloud can always shift even more in one direction than it normally would to create even larger quantities of partial charge temporarily to make the attraction stronger. So that's always underlying everything. And then we've got dipole-dipole. Because the molecule is a dipole, it has a positive end and a negative end, and two molecules can line up their oppositely charged ends. In the second structure, we definitely know there's a dipole, primarily more negative at the top and more positive at the bottom. So a second structure that's identical could come in here and form a dipole-dipole. So there's always London forces. In this case, there's also dipole-dipole. I know that because the negative end of one can attract to the positive end of the other. So if this oxygen's negative starts to attract to the carbon's positive, that's a dipole-dipole attraction. But there's also hydrogen bonding in this case. Where is the hydrogen bonding? Well, there's two different areas where that could form. One is between the hydrogen and the oxygen lone pair. Right? This hydrogen sharing electrons with the nitrogen. The nitrogen's much more electronegative, and the hydrogens carry a large partial positive. Only nitrogen, oxygen, and fluorine are electronegative enough to create that much partial positive on a hydrogen. But since we have one of those three elements here, this hydrogen will have a large partial positive, and there will be a nice strong attraction between the large partial negative of the oxygen's lone pair and the large partial positive of the hydrogen. You could also imagine a hydrogen bond here between the large partial negative on the nitrogen and the large partial positive on the hydrogen. So that would just depend on where the molecule ends up aligning itself. There's a couple different ways you could imagine a hydrogen bonding there. The third structure, definitely London forces, since those always exist whenever there's an electron cloud randomly shifting around. Yes, on Tuesday we said this was nonpolar. So you may say, well, if it's nonpolar, it doesn't have a dipole, so it can't undergo dipole-dipole. That's fine if you want to think of it that way. But we also should recognize that the nitrogen-hydrogen bonds have large electronegativity differences. So there are local regions within the structure, this region here, that has a dipole, even though overall it may be symmetrical and the dipoles cancel out. And there's another region here where, because of the electronegativity difference, we've got large partial charges. So this has a dipole. So you could think of this individual region of the molecule being a dipole and setting up to attract to a neighboring molecule's dipole. And so you could also label this as having dipole-dipole. So if your quiz answer included dipole-dipole for that, or if it didn't, I didn't mark off either way. Definitely, though, you need to include hydrogen bonding for this particular structure, because there is a large partial negative on one of the three most highly electronegative atoms, and there's a large partial positive on a hydrogen, and so those can attract from one molecule to the next. Etc. I don't have space to draw the structure in there, but hopefully you get the point. One molecule next to a neighboring molecule, the large partial negative of one on a highly electronegative atom, attracting the large partial positive of a hydrogen that's largely positive because it's sharing electrons and they're being pulled away from it by a highly electronegative atom. That one sets that one up for hydrogen bonding. Whether or not molecules will mix is largely in part due to their polarities and the types of intermolecular attractions they can form. So we have this general rule, like dissolves like, and we want to talk about that in a little bit of detail. So here's a couple scenarios. Let's say I've got some compounds mixing and they're all capable of hydrogen bonding. Well, then I should think logically there's no reason why they shouldn't mix. Right? So if I have, for example, water molecules are capable of forming nice strong hydrogen bonds with other water molecules, large partial positive, large partial negative. Those are pretty strong attractions. So if I want to mix some other molecule in and expect it to get in between there and attract, it better have similarly strong attractions, otherwise the water molecules' hydrogen bonding attractions are going to cause them to stick together and exclude the other substance from mixing in. So if the other substance, maybe methanol, is allowed to come in contact with that, well, it also has areas of large partial negative and positive, so it can also hydrogen bond with the water. Water molecules are capable of forming up to 4 hydrogen bonds. Each lone pair can attract to a hydrogen from a neighboring molecule, and each hydrogen can attract to a lone pair from a neighboring molecule. So you might think, well, if this is capable of forming more attractions, the methanol is only capable of forming 3 hydrogen bonds because it's got 2 lone pairs and one hydrogen with a large partial positive. The CH3 group doesn't really affect the hydrogen bonding because there's no large partial charges there. So you might say, well, if the water molecule can form up to 4 hydrogen bonds with other water molecules, wouldn't that be better than allowing this thing to come in and mix in when it can form not as many hydrogen bonds? Well, the answer is yes. So why don't the water molecules stick together with one another where they can form a greater number of hydrogen bonding attractions and exclude the methanol? Anyone got an answer for that? Well, the answer there is entropy. And so we know from Gen Chem 2, entropy is to do with variety and randomness. And as long as these two are both in the liquid state, the individual molecules have a lot of motion, and that motion tends to create more variety and randomness. So even though this can form more hydrogen bonds, if these molecules are bouncing around and moving around, and these molecules are bouncing around off of one another, eventually all of that motion and bouncing is going to cause everything to mix together relatively thoroughly. So these two should be soluble or miscible because they're capable of forming similarly strength attractions and because entropy generally favors mixing. If I mix two nonpolar substances, entropy is also at play there. So if I ask you about whether or not, say, this molecule should mix randomly and thoroughly in with something like this. Put some double bonds in here so I don't have to draw as many hydrogens in. Well, these two structures are both nonpolar. Neither one's capable of forming really very strong attractions with anything because none of them have really any large partial charges. So the question here is, why wouldn't they mix? Right? If they're both bouncing around randomly and entropy is a factor, it's going to cause everything to be more random and cause more variety, and that's going to result in mixing. So if both substances are nonpolar, they mix readily because of entropy. If both substances are highly polar and or capable of strong hydrogen bonding or especially strong dipole-dipole and they have large partial charges, they'll mix both because of entropy and because the charges will just be able to attract. So then the question is, what about trying to mix something nonpolar in with something polar? That's where we run into a situation where they won't mix very readily because even though entropy would normally predict everything would be more random and mix in randomly and thoroughly, the large partial charges here on the water molecules keep them together. And if this nonpolar thing came in here and was only able to form some weak London forces with the water molecules, that wouldn't last very long. The water molecules would push that back out so that they can get their areas of partial charge closer together and attract to one another and kind of stick together. So that's why oil and water don't mix. The oil is nonpolar. The water molecules attract one another quite strongly through hydrogen bonding, and so they just exclude the oil because when it does get down in there, they push it back out and form their stronger attractions with one another instead. Some molecules, known as surfactants, have large nonpolar areas as well as a highly polar. In this case, it's not technically polar, it's actually charged, which is like even more polar than polar. Because I've got a full charge here, this is going to form a really strong attraction with a water molecule. Normally we think of water molecules attracting other water molecules pretty strongly because of the large partial charges involved. But here I've got a partial charge, full charge attraction, and that's really even stronger. So this is an interesting molecule. It has one area that can attract strongly to water, and it has another area that cannot attract very strongly with water. Right? If this large nonpolar area were to enter into water and be dissolved by water, well, the water molecules with their large partial charges would be like, I can't form a strong attraction here. And if there's other water molecules on the other side, which there would be because if it's dissolving and everything's mixing in close quarters, this water molecule would just force this nonpolar area out so that it can attract to another water molecule. So water molecules don't technically repel nonpolar molecules. There's no like actual repulsion like positive or negative repulsion. There's just a stronger tendency to attract other polar molecules, so the nonpolar molecules get pushed out so that the polar ones can attract each other and form stronger attractions. So the result of that is all the areas of charge form nice strong attractions to water, and all the nonpolar areas get pushed away from the water. And they get pushed away from the water, so there'd be water out here. This would be my solvent surrounding this thing. All the nonpolar areas represented by these little squiggles get pushed out away from the water to the interior of the spherical structure. And all the green ones are the charged, negatively charged ones. They stick onto the surface so they can attract to the large partial positive of the water. And that is how soap works, right? If you try to clean your skin, maybe you got some olive oil or something greasy on your skin, you want to clean it off. You can't just rinse it with water because water molecules attract to other water molecules better than they attract to grease or oil. They're not going to surround the oil on your skin and rinse it away. But if you lather up with some soap, all that lathering motion, the rubbing and friction of your hands will allow the oil to get inside these micelles surrounded by these other low polarity molecules, and then the charged areas on the outside of that attract to the water, and that whole thing can get rinsed away by the water. And that's the cleaning action of surfactants or soaps. Any questions about any of that? Alright, so let's see if we can answer these questions now that we've talked about that. First question, which attraction is stronger? The attraction between a permanent dipole and an induced dipole, or the attraction between a temporary dipole and an induced dipole? So 1 or 2, which is stronger?
The first one.
Good. One brave soul wanted to answer that correctly. Nice work. So the first one is stronger because a permanent dipole implies that you've got a structure with a permanent difference in electronegativity, like HCl, like we talked about that as a simple example. Pretty decent electronegativity difference, so this end is always negative, this end is always positive. An induced dipole is where a normally nonpolar structure, something like methane, for example, because it's symmetrical, it doesn't have opposite charges on opposite ends. Well, how can it even attract here? Well, we said that would be London forces. So this is one example of London forces, where a nonpolar molecule doesn't have the ability to attract unless the electron cloud shifts to one side and creates temporary partial charges. But that shifting will be induced to happen because of the neighboring charges on the neighboring molecule. Right? So the negative here pushes the electron cloud away, exposing some nuclei with some positive, and then that allows for an attraction to form. The difference here between that and scenario 2 is the temporary dipole would be a situation on a molecule that's not normally polar. So this could be an example where maybe two different methane molecules attract. If neither one has a permanent polarity because they're both nonpolar to begin with, then I don't have any charges unless one of the molecules randomly happens to shift electrons to one side or the other, and then that would cause the electrons in the neighboring molecule to shift and allow for the attraction. So that is also an example of London forces. So London forces are any time where at least one of the molecules doesn't normally have a dipole and it shifts temporarily. So if that happens for both molecules, the quantities of charge are usually going to be small and they're going to be temporary, so the attraction is weaker. At least if one of my molecules is a permanent dipole, then at least some of the charges will be permanent, and that will allow for a more long-term, not permanent by any means attraction, but a more long-term partial charge attraction, which will make it stronger. Good. So let's look at the second one then. What should be stronger, the attraction between a polar molecule and a nonpolar molecule, or the attraction between two nonpolar molecules?
Two nonpolar.
Yeah, so almost every time when we go through this, students don't get this correct. So don't feel bad about that, because we just talked about like dissolves like, so it's probably in your mind you're thinking, well, if polar and nonpolar don't dissolve, then they probably don't have a very strong attraction, whereas if two nonpolar molecules do dissolve, they probably do have a pretty strong attraction. But the second question here is really the same as the first question. A polar molecule is one that has a permanent dipole. A nonpolar molecule can only form a temporary dipole. Two nonpolar molecules will both only have temporary dipoles. So the second question is really the same as the first, and the answer is the same as well. So even though polar and nonpolar molecules don't dissolve in one another, they still have an attraction. It's a dipole-induced dipole attraction, because the polar molecule can cause the electron cloud in the nonpolar molecule to shift in a way that allows them to attract. That's going to be a stronger attraction usually than the attraction between two nonpolar molecules. So if we only think about the attraction, you might think, well, how come these don't mix then? Well, the answer is because if I've got the polar structures, they have the permanent dipoles, and they're better at attracting with one another, so they usually just stick together and exclude the other substance. So even though they can attract the other substance, if they attract one another stronger, that will push the other substance out, and they'll stick together exclusively with others of the same type. In the case of the nonpolar, the attraction is very, very weak. It's the weakest type of attraction we have. But they still mix because of entropy, because they don't have to give up any strong attractions in order to mix. They're just bouncing around randomly, and whether they break the attractions they already had and form new ones or not, it doesn't really matter, because none of the attractions are that strong. So the randomness created by the motion causes them to mix despite not having very strong attraction. Any questions about that? Right, so hopefully that clarifies that for you. And so this is kind of a capstone on that topic. Why won't non-compounds readily dissolve in water? Is it because water molecules repel nonpolar molecules? No, that's not the reason. A nonpolar molecule does not repel water, right? Water has opposite charges on opposite ends. No matter what it comes in contact with, it can form an attraction. If it comes in contact with something that has a full negative charge, it'll adjust itself so that the positive lines up with that and attracts. If it comes up next to something with a positive charge, it would flip around. The molecule would just flip around, and the negative would come in and attract. So it can attract to charged particles. It can attract to polar molecules. If I had like HCl, partial positive, these would just naturally, kind of like magnets, they just kind of line up next to one another to allow their charges to attract. And likewise, it can also attract to nonpolar substances. So if I have a water molecule with a negative end and a positive end, any nonpolar structure can attract to it. Something like methane or something like hydrogen, whatever nonpolar structure you want to come up with, the electron cloud in that nonpolar structure can always shift around. And so it can shift in this direction to create the charge necessary, create more negatives on one side to attract the positive. It can shift away to allow some exposure of some nuclei there to attract the negative. So there's always a possibility for attraction. There's no actual repulsion. So the reason why they don't readily dissolve is because the water molecules attract other water molecules even more strongly. So there's a decent attraction here between the polar water and these nonpolar molecules, but there's a much stronger hydrogen bonding attraction between water molecules, and that much stronger attraction brings all the water molecules together and by default excludes the nonpolar substances because their attractions are much weaker in comparison. Alright, so that's the end of chapter 1, and I'm pretty sure exam 2 covers day 2 and day 3 material. So next week you're going to have an exam on what we talked about this week. And just to clarify, for those of you who normally have lab on Monday, this coming Monday is obviously Labor Day. We won't be meeting on campus at all. So the Monday group of students are going to be tested on the day 2 and day 3 content the following Monday. So the first people in the class who will have an exam on this day 2 and day 3 content will be the Tuesday group, and then the Wednesday, Thursday group of next week will have an exam on that material, and then the Monday people the following week. So the Monday people will be behind by a week when it comes to exams until the week of Thanksgiving. During the week of Thanksgiving, later in the semester, the Monday people will have an exam that week and the others won't, and that will allow everything to get back to normal throughout the rest of the semester. So this day 2, this first few sections of the first few sections of chapter 2 here are on the day 3 material, so they are relevant to what you might be tested on next week. So we'll talk about how to draw and represent molecules. So there's a few different ways you could see a molecule drawn out. The Lewis structure is probably the most complete. It shows every atom. It shows every single bond, so you know exactly which atoms are bonded to which atoms. No confusion about that whatsoever. It includes all the lone pairs, so we're showing every single pair of valence electrons that should exist in the structure. However, it takes a long time to draw all these bonds, and you can see I'm already sick of drawing hydrogens year after year, so my hydrogens got sloppier and sloppier, unfortunately. So this is not preferred way for chemists to draw structures, even though it gives you all the information, just because it takes a lot of time to draw out all the hydrogens, and it starts to look cluttered. And a lot of times carbon-hydrogen bonds are really stable, and they don't really involve themselves in reactions. So a lot of times we don't want to draw them because it's just a distraction from the area of the molecule that might actually undergo a chemical change by breaking or forming bonds. So another way to at least make it a little easier to draw the structure is sometimes when the carbons and hydrogens are bonded, instead of showing those bonds, we'll show how many hydrogens there are on that carbon. So it's kind of condensed, or at least partially condensed structure. So it still shows some of the main bonds, so you can kind of see the shape a little bit, but you want to get used to seeing this as well. If you see hydrogens shown next to the atom, that's the same as showing the hydrogens bonded to the atom. Same thing, just a different way of representing it. A fully condensed structure also has the structural information. So this is a tricky thing for students to get used to. It takes some practice, so definitely recommend you practice some of these from the textbook. This representation is meant to be the same as the Lewis structure. It's just we're not showing the bonds. So from this you have to be able to infer where the bonds are. Right? So here anything in parentheses is implied that it is attached to the neighboring atom. So here this carbon here, this one here, has 2 CH3 groups attached to it. It doesn't matter exactly where I position them in space. That's a topic for another day. That carbon also has a hydrogen attached to it, and it has an OH. And then I would recognize there are lone pairs that are necessary to make its noble gas configuration. So this structure is the same as this one. It's just kind of rotated on its side, and the angles look a little different. But that's something we'll talk more in detail about later. So we're not worrying about the angles right now, and we're not worrying about where in space the atoms are pointing. So this is This has all the structural information. Because of the way it's written, I can tell there's two CH3 groups bonded to that carbon. That carbon also has a hydrogen, and it also has an OH. The molecular formula, though, doesn't give me any structural information. So you want to get used to that as well. If I just tell you how many carbons, how many hydrogens, and how many oxygens, and I haven't given you any information about how they're connected, that doesn't really tell you what the compound is. Because to bond 3 hydrogens, 3 carbons, 8 hydrogens, and an oxygen, there's lots of different ways I can do that. I can put the 3 carbons with the oxygen on the outside and then put the rest of the hydrogens in there. This is propanol. This is isopropanol. They have different boiling points, different reactivities, different properties. They're not identical. They're isomers. And just telling you the molecular formula doesn't specify which of those two we're talking about. So if I just give you a formula, there may be multiple correct answers that are reasonable. I could also, for this formula, I could also draw something like this. I could put the oxygen between carbons. And then when I put all 8 hydrogens in the lone pairs, I have something called methyl ethyl ether. That has totally different properties. This one can't hydrogen bond with other identical molecules like the ones with the OH group can. So their boiling points are lower, their properties are different. So just to reiterate, the formula doesn't tell me how things are connected. Any one of these types of drawings does show me how the atoms are connected and is specific to one individual compound, whereas the formula could represent a number of different isomers. So technically, all 3 of these give me the same amount of information. It's just I have to interpret the way these are drawn to get that information out of the formula that's given. So you want to definitely get some practice with that. Here are the 3 isomers that we just drew. Again, these all have the same formula, C3H8O. They're all unique. Each one has a different name. Each one has a different property. Each one has different reactivity. They're not the same structure, right? So isomers are different compounds made of the same atoms, but they're bonded different structurally, and that gives them different properties. So if I want to be specific that I'm dealing with this compound, I could tell you the name of it, but we haven't talked about naming yet, so I wouldn't do that yet, obviously. I'd have to give you some structural information, so I could tell you, I could draw the Lewis structure, or I could do one of these partially condensed structures, or as we're about to see a little bit later, I could also do the bond line representation. And the bond line representation is by far the most common way organic chemists communicate about structures. So we're definitely going to focus on that a lot, and you want to practice that a lot before next week. Because it will be likely to show up on your test. So here's my pitch for why we use the bond line structures. And it's especially important here where you have a big honking molecule like this amoxicillin molecule. So this is the structure of one specific antibiotic. You can see there's a ring of carbons here, a bunch of CO double bonds, some nitrogen, sulfur added in there. And if I draw the Lewis structure, first of all, it's going to be difficult for me to do that by hand because none of my lines are going to be straight and all these atoms are really close together. It's hard to tell what's bonded to what. And when I show all the hydrogens, it just takes forever to draw those in. The larger the structure, the more of an imposition it is to have to try to draw out the Lewis structure, the full structure with all the bonds shown. So this is too much of a burden. Organic chemists are way too lazy to have to deal with this on a regular basis. So what we would do is to draw the bond line representation or the bond line structure. And in the bond line structure, every carbon just becomes a point. I don't have to show the carbon atoms label. And every hydrogen disappears. I don't have to draw it at all. And so by leaving out the hydrogens, we're not suggesting they're not there. We're just saying if you know anything about organic chemistry, you'll know how many hydrogens there are because you know carbon will pretty much always have 4 bonds. If carbon doesn't have 4 bonds, it would have to have a charge shown on it. if I have a carbon with 3 bonds and a lone pair, it's going to end up with a negative charge. That would have to be labeled on the bond line structure. So if there were no hydrogen here and I intended there to be a lone pair, well, first of all, I'd draw the lone pair in, but I would also have to label that that carbon has a formal negative. Alternatively, if a carbon has 3 bonds and no lone pair, then when I calculate its formal charge, it ends up being positive. So you may see that. We'll see that a lot later in the semester. But if I had a carbon that only has 3 bonds shown, I'm to assume the 4th bond is to a hydrogen, unless there's a negative charge in a lone pair, which would imply it should only have 3 bonds. Or if I show a positive charge, that would also imply that it should only have 3 bonds. So I would recognize that there's no hydrogen at that spot. So I wanted to point that out. Typically though, most carbons will not have a formal charge of positive or negative because that is really pretty unstable, especially the negative. So unless you see a positive or negative, you can assume the carbon has 4 bonds, and that means it will have as many hydrogens as it needs to make 4 total bonds. So if there's 1, 2, 3 shown, you know the 4th one has to be to a hydrogen. So we don't have to draw that in. And by not drawing it in, the structure looks much cleaner. I can very easily see where the hetero atoms are, the non-carbon and hydrogen atoms, the oxygen, the nitrogen, the sulfur. My eyes are drawn to those. I can quickly see that there's a 4-membered ring here, which wasn't necessarily very easy to see because of all the clutter in the molecule above. So as you practice these and get used to them, you will find that the bond line structure is a superior way to quickly draw structures and to communicate about their structural information in an effective way. So it looks like we're leaving out a lot of information, but once you get used to inferring that information from the structure, it'll become natural to you. But that will only happen if you practice. So you definitely want to practice a lot of these, a lot of the practice problems related to this. And like I said, it kind of will seem weird at first, like a foreign language, to look at this and recognize where all the carbons are and everything. But your brain will get used to seeing that. And it is the main way that we will communicate about structures moving forward. So the sooner you master it, the less confusion there will be for you when we're talking about structures throughout the semester. So what are the basics for bond line structures? How do we communicate about molecule structure with these types of representations? So the idea here is, if you see a zigzag like this, you're to interpret there being a carbon at the wherever a line ends and wherever there's an angle or a bend in the line. So this molecule has 6 total carbons. What about this? I've got something like this. Here's a mistake that students often make. If this is my bond line structure, what students will sometimes do is say, okay, there's a carbon here where the line ends. There's one here where the line, where there's an angle, or where it bends. Another one here where there's another intersection between 2 lines, or where it bends. And then sometimes students will try to jam carbon in there. That's not right. So if a line is straight and heading toward a different atom, that's implying there is no carbon there. So don't insert carbons at the end of a line if the line actually ends on a different atom. That means there's no carbon there. It's just a bond between this carbon and this oxygen. So that's the way you want to think of that. So wherever a line ends, or wherever 2 lines intersect, or where it bends, there should be a carbon there. So this is 6 carbons. And we know that there's enough hydrogens to make each carbon's noble gas configuration. So if a carbon only has 1 bond to it shown, it still needs 3 more bonds, so there'd be 3 hydrogens. And I hate drawing these in, so we just count the rest up by just drawing lines, if you can follow me there. And so that gets me to 14 hydrogens. We try to show the angles pretty close to what they should actually be. So in this molecule, if my carbons are sp3 hybridized because they have a steric number of 4 due to the fact that they have 4 sigma bonds and 0 lone pairs, the angles on an sp3 hybridized carbon should be about 109. degrees. So we don't want your angles to look too sharp. We don't want them to look like 30 or 40 degree angles. We don't usually want them to be too obtuse, where they look like they're close to 180 degrees. We definitely don't want your lines to be a full 180 degrees, because then that looks like one line instead of two separate lines. So try to make your angles relatively close. Just make them look a little bit bigger than 90 degrees whenever possible. Just to point out, if I have a structure that involves a triple bond, something like this, the angle here actually should be 180. So if I were drawing this into a bond line representation, I'd have a triple bond, and then the single bond will be coming 180 degrees out. So in that case, I would not show an angle, and we'll see another example of that in a minute. As we said, the hydrogens are omitted. How do we know where the hydrogens are? We just talked about this. There are enough hydrogens at each carbon to complete its noble gas configuration, so usually students don't have too much trouble with that. Why are we omitting them? For the sake of time and energy, and also to make the structure look a little bit neater. Right? It looks more like the shape of the molecule than it would if I put all these extra lines in there and bonded them in different directions. Alright, so sometimes you might have some carbons coming off as a branch point. Right, so the same rules still apply. There's a carbon wherever a line ends. And there's a carbon wherever two lines intersect or wherever there's a bend. So when you see a bond line representation, in your mind, you don't have to, in the beginning it might be a good idea to draw the carbons in there and maybe even number them. But as you get more and more practice, your mind will just start to see the carbons in those positions. You'll know that they're there, and you'll be able to count them and number them without actually drawing the atom carbon on those points in space. So each one of these has 6 carbons. Each one of these has 14 hydrogens. So these are 3 different isomers of the formula C6H14. This one, if I were to draw the condensed formula, I might ask you to do that. This one has a CH3 bonded to a CH2, bonded to a bunch of other CH2s. So I could draw those CH2s out and put the CH3, or I could put them in parentheses. Since there's 1, 2, 3, 4 of them, I could type 4 of those, and then the other CH3. So either of these is also an appropriate way to show the same structure. For this one here, this carbon here has 2 different CH3s bonded to it. So probably the one CH3 is bonded to this carbon right here, and the other CH3 is also bonded to, so there are 2 of those bonded to that carbon. Let's just number these so we keep track of them. I feel like otherwise we'll lose people. So these 2 represent carbons 1 and 2. This is carbon 3. Carbon 3 has 1 hydrogen because there's only 3 bonds shown. I know there has to be 4 unless there's a charge, which there isn't. And then carbons 4 and 5 are both CH2s, so I could draw 2 of those, or I could just draw 1 and put a 2 here to indicate that there are 2 of them, and that would be 4 and 5. And then carbon 6 is a CH3 there on the end of that chain. Here, my carbon 2 has 2 different CH3s bonded to it. I don't want to put this here because it makes it look like there's 2 carbons. Carbon 2 has a hydrogen. It's bonded to carbon 4, which has a hydrogen, and then that's bonded to 2 more CH3 groups. So that would be a condensed way of showing the same structure. And so this is not used often by chemists. This condensed structural formula, it takes a while to draw out. It's not intuitive. It doesn't really show you the shape of the structure. That's why we like the bond line representations, because they show you the shape, they show you how the atoms are connected, but you just have to infer where the carbons and hydrogens are located. If you have a double bond, the angle here should be pretty close to 120. Right? A double bond, there's a hydrogen here, it's not shown in the bond line structure, but just to point out, a double bond has sp2 hybridization, because that carbon has 1, 2, 3 sigma bonds and 1 pi bond. So if there are 3 sigma bonds, add up the 3 sigma bonds, the steric number is 3, it's sp2 hybridized, and when it's sp2 hybridized, the angles are about 120. So in that structure, try to draw it so the angles look roughly 120. We don't need to put the hydrogens in. We know there's going to be 3 hydrogens on each end to make 4 bonds for those carbons. And the central carbons are going to have 1 hydrogen to make 4 bonds there. Right, so this is going to be C4H, 1, 2, 3, 4, 5, 6, 7, 8. C4H8 would be the formula for that particular structure. The bond line representation is nice. It shows you where the double bond is. Right? There's my bond line representation for that structure. If I were to draw a condensed structural formula, I'd have a CH3 on the end. I'd have a CH here. I'd have a CH here. And then I'd have another CH3. You might see someone write a double bond in there to show that. You might not. So with the condensed structural formula, sometimes they don't show the double bonds or triple bonds. It's hard to know exactly what the structure looks like. The bond line representation is much superior to that. And it's way faster and easier and cleaner to draw than a full-on Lewis structure. As we mentioned earlier, if you have a triple bond, the angles should be 180. Here, the steric number is 2. Each carbon has 1, 2 sigma bonds and 2 pi bonds. Talked about that last time. So the pi bonds don't count toward the steric number. Only the sigma bonds and lone pairs. If there's 2 sigma bonds and 0 lone pairs, that gives me a steric number of 2. It's sp hybridized, so the angles should be 180. And so I don't want to see triple bonds looking like this. Generally, I don't take off points for that. It's just slightly irritating. The angles on an sp hybridized carbon are 180, not anything less than that. So try to draw your triple bonds in a linear format, because we want our bond line representation to represent the shape of the structure as closely as possible. Any heteroatom, which is an atom that's not carbon or hydrogen, needs to be shown in your bond line representation. So if I have an oxygen, I've got to include that. And if there's any hydrogens bonded to the heteroatom, those should be shown as well. So just to be, if we didn't include the oxygen here, and we just drew the double bond, well then you would infer that there's a carbon there. Right? Wherever a line ends, even if it's a double bond, it's still a line. Wherever it ends, you'd assume there's a carbon. So if there isn't, and there's something else, you got to draw it in that bond line representation. It's also good to get into the habit of drawing in the lone pairs. Sometimes I don't do that just because it's easy and faster not to, but it's a good habit to try to get into drawing those in. And then when you see the bond line representation, again, you know each carbon needs 4 total bonds, so you know that there's 2 hydrogens on any carbon that only has 2 bonds shown, and 3 hydrogens, obviously, on any carbon that only has 1 bond shown. How many hydrogens are on this carbon right here? 0, right? It already has 4 bonds shown, so I know there's no hydrogens there. I can't have a 5-bonded carbon. Alright, so let's do a little practice to give you some looks at some slightly more advanced molecules. We'll talk about the quiz question, and then I highly recommend you practice even more of these to make sure you've got it down, especially before next week. So here, how many carbon atoms are there? So we could number them. Is there a carbon atom right here? At this point, no, because this line is ending on the sulfur. So there's no carbon there. The first carbon would be right here. So we'll call that carbon 1. There's a connection between lines here, so this is carbon 2. There's a carbon right here. I've got this sigma bond here, and then I've got a triple bond. So there has to be a carbon there with a single bond on one side and a triple bond on the other side. That provides that carbon with 4 bonds. So we'll call that 3. This one's 4. 5. There's one here. 6. Where a line ends, there's always a carbon. Where there's an intersection between lines, there's a carbon. So I got 15 carbons. And then I want to count how many hydrogens there are. So my molecule's all cluttered up. I want to get rid of this so I can then draw in the hydrogens. If I'm going to count them, it really is way easier to actually draw them in so you don't miscount. So I'm drawing in the hydrogen. Don't forget to count the ones on the heteroatoms. Don't just count the ones you drew in. So don't want to forget about that one. So there's 1, 2, 3. Is there a hydrogen here? No. It's already got 4 bonds shown. Is there a hydrogen here? No. It's already got the triple bond and the single bond, 4 bonds shown. There is one here, because this carbon only had 3 bonds shown, so that'd be 4. Nothing here, 4 bonds already shown. 5, 6, 7. We should probably put hydrogens there. 3 hydrogens here, because there's only one other line shown for that carbon. No hydrogens here. It's going to be 1 here. It's 3 bonds shown. I need a 4th 2 hydrogen, so I call that 8. No hydrogens here. No hydrogens here. So wherever there's a line that just ends, that is a 3 hydrogens on that carbon to make 4 bonds. So we call that 9, 10, 11. Same thing here. 12, 13, 14. Here there's 2 bonds shown, so I need 2 more, 15 and 16. Nothing here. And then here, 3 more hydrogens to complete that carbon's noble gas configuration. So that gets me to 17, 18, 19. So I believe it counted up all of the hydrogens there. It's not very common to end up with an odd number, so I'm feeling like I may have miscounted. I'm just going to count them up real quick again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Yep, looks like 19. Questions about that one? So here was the quiz question. Most of the answers I saw you working on were correct here. We'll just make sure we all understand it. So I want to number the carbons. Obviously there's no carbon here because this line ends at the oxygen. So this line here is ending in space though. So there's definitely a carbon there and there. And then we have 6 in the ring. 4, 5, 6, 7, 8, 9. And then 2 more, 10 and 11. So there's 11 carbons. If we want to count the hydrogens, we get rid of these labels so we can draw them in. So I could really start wherever as long as I draw them all in. Maybe it's just easier to draw them all in before I start counting. I got a little trick on the last one. So I just want to maybe draw all these hydrogens in. So every carbon that I labeled has 4 bonds shown to it after I draw all of my hydrogens. So now I can count them up. 1, 2, 3. Oh, I forgot to draw. Yeah, it takes a lot of diligence to make sure you're finding every carbon that doesn't have 4 bonds shown and getting all the hydrogens in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that is usually not too troublesome for students to see a bond line representation and count the carbons and hydrogens and know where they are, although it does take some practice, so I definitely recommend you at least practice a few till you feel like you've got it down pretty well. Where students do have some issues sometimes is if you're given a Lewis structure, how do you interpret that into a bond line structure? Right. So obviously, if I got 4 carbons, I need a zigzag that puts a carbon at the ends where the line ends and at the 2 intersections. So that would give me the 4 carbons I need there. As we said before, avoid angles that are really short and spread out the atoms. That will give you a structure that represents the correct angles more closely. I also mentioned, but we'll reiterate, the angles don't really matter, right? So the single bonds can always rotate. So if I have this coming up at an angle, it's not really any different from having it come down at an angle, right? So if I were to rotate this group would be, it could easily rotate down into that position. I still have the same roughly 190-degree angle that I had before, so it doesn't really matter how I draw it. So this structure here is the same as this, and it's the same as the other one that was there initially. Those are the same molecule, they have the same name, and they'll interconvert due to the rotation of the single bonds. So we could draw alternative versions of this same structure as well, just by rotating. Right? So I could start by rotating this bond. If I rotate there, the rest of the molecule is staying steady. Just rotating this, and this CH3 group will flip down like that. So this structure is the same as that one. Or instead of rotating here, I could rotate here. So if I keep the right hand side of the molecule the same, when I rotate this down, this is also the same, right? If I want to check it, I can just number the carbons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So the way that things are oriented in space is not that important right now. We'll talk about that in detail later. For now, you want to recognize that depending on how the bonds are rotated, things can flip around. And I could take this structure here and rotate this. I could take this whole part and kind of flip it over to the other side. And so that would give me something like this. Oops. I'm going to draw that up here. Yeah. Same structure. It's a CH3 followed by 3 CH2s. You got CH3 followed by 1, 2, 3 CH2s, and then the CH with 2 more CH3s attached there. Right, so same numbering. So you want to be aware that things can flip over in space. Probably practice that a little bit too. I'm sure there's some practice problems in the textbook related to that. So if you have a Lewis structure and you want to draw in a bond line representation, start with the carbon chain, draw out your zigzag, count the carbons, especially on the exam, just double check all your work, make sure you have the correct number of carbons, make sure any other elements are attached at the carbon that they're supposed to be attached to. Never draw a carbon with more than 4 bonds. So, you know, obviously, don't make a carbon with 5 things coming off of it. That could never happen. Don't make a carbon with a double bond and then another thing coming off of it. That could never happen. Right? So make sure your carbons are limited to 4 bonds. So let's practice a couple here, see if we can draw a couple more bond line representations. So here I've got to show the chlorine. It's not a carbon, so I can't just omit it. But I want to start my zigzag with my carbon, so I'm going to number these first. I like to start with the carbon skeleton, the zigzag part of it, and then I can decorate that with the other elements if there are some. So I've got 1 and 2, 1 bonded to 2, 2 is bonded to 3, 3 is bonded to 4 through a triple bond. So I want to keep the same line going. I don't want to bend that because the triple bond is linear or 180 degrees. So I'll just start numbering these so we keep track. 4 is bonded to 5, and that one's also 180 degrees. So I need to keep that all going in the straight line around my triple bond because both parts of the triple bond are sp hybridized. Then 5 is bonded to 6 through a double bond. So 5 and 6. That where I do want an angle because that's sp2 and it should have 120 degree angles. And then 6 is bonded to 7. So there's that structure. Now all I have to do is add the chlorine to carbon 1. So when I add the chlorine, I can have it coming straight down. I can have it coming up. I can't have it coming here at the same angle. And if I draw it here, there's no way for you to know there's a carbon there. But there is. That's carbon 1, right? So I can't do that. I got to draw the chlorine at an angle. So since I have my 1 already there, kind of blocking that, I'll just have it come down at an angle. Since there's a little bit of an angle here, I can recognize there's a carbon there. So there's a bond line representation for that structure. If I want to draw one for this structure, I want to number my carbons. And sometimes it's easier to first number the ones in the chain and then later number anything that's kind of hanging off the side. I give a number to every carbon. So I'm going to start with carbon 1 now. 1 is bonded to 2. 2 is bonded to 3 through a double bond. I'm doing the zigzag, representing the correct angles. 3 is bonded to 4. 4 is bonded to 5. 5 bonded to 6. 6 bonded to 7. 8, 9. And a 4-membered ring. Right, so 9 comes back around and bonds back to 6. I'll extend my numbering just to make sure the numbering matches up, which it does. And now I have to account for carbon 10. That's bonded to carbon 2. So there it is. Carbon 11 is bonded to carbon 4. So there's carbon 11. So that accounts for all my carbons, but I have an OH group on carbon 6, so that should be shown. I have to draw in the oxygen and the hydrogen that's bonded to it. Always draw in the hydrogens that are bonded to hetero atoms or non-carbon atoms. Any questions about that one? All right, so a couple more examples here, and then we'll talk about the quiz question, and then we'll be done. So I want to draw some possible isomers for this formula. So this is where you can start by drawing Lewis structures and then translate those Lewis structures into bond line structures, but I recommend practicing this by just starting with the bond line structure. So if I've got 5 carbons, I might start by just doing a zigzag that gives me 5 carbons. 1, 2, 3, 4, 5. Then I got to put a chlorine and an oxygen in there. I don't really care where they go. I'm just going to put them in and see what happens. So there's some trial and error here. Maybe I'll put a hydrogen on there so the oxygen makes its octet and doesn't have any formal charge. So does that bond line representation match the formula? Well, it's got 5 carbons, a chlorine, and an oxygen. And I gotta get rid of this garbage. So does it match? Well, I have to make sure that the hydrogen number matches. So here I would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this has 11 hydrogens. It's got too many. So it does not match the formula. So if I've got 11 hydrogens, what can I do to my structure to get it down to 9? Oops. Okay, I don't know what that was. See if I can get out of that. Oops. I don't want that. Cancel that. Go back in. Alright. What I was trying to do was to get this eraser, which I can't do now because that's permanent. Okay, let me just restart that then. Alright, so we have this structure. It's got too many hydrogens. It's got the right number of carbons, the right number of chlorines and oxygen, but it's got 2 hydrogens too many. So how do I get rid of 2 hydrogens? I make a double bond. I can make a double bond between any of these carbons, and that will work. Just pick 2. I'll pick these 2. Make a double bond. Now when I count the hydrogens, I got 1, 2, 3, 4, 5, 6, 7, 8, 9. So now my structure matches. When you draw your bond line representations, don't draw the hydrogens in with lines, because that's not a bond line representation anymore. It's helpful to draw them in to count them, but make sure that you delete them afterwards, because otherwise it's going to look like those are carbons at the end of those lines. So I have to get rid of these hydrogens, otherwise my structure looks really incorrect. So there's one possible bond line structure for that particular formula. So another one I could have created by putting the double bond somewhere else. Maybe I'll put it on the end. You can start to see how I can draw a lot of these pretty quickly without having to take the time to draw all the hydrogens in. I could put the double bond somewhere else. To make an isomer, I could move the chlorine to a different atom. I could just draw the carbon skeletal structure the same. I could have moved the OH to a different atom. I could move the chlorine to a different atom. Right? So you can imagine there's dozens of different isomers you could draw from this formula by putting the double bond in a different position or putting the chlorine or OH groups on different carbons. You want to bear in mind as well that carbons can form rings. As long as the rings are not less than 5 carbons, they're usually relatively stable. It is possible to make smaller rings, but it doesn't happen very often. So just to point out really quick, I could make my 5 carbons into a pentagon. Right? At every corner there's a carbon. That's 5 carbons. So then I put my chlorine on, I put my OH group on, and that also has 5 carbons, 9 hydrogens, a chlorine, and an oxygen. So this is also an isomer of each one of these other isomers that we already drew. If we're talking about rotational conformations, we're talking about how the bonds are positioned in space. So if I've got this structure here, this is a messed up structure. I can't have a CH2 on the end of my structure. Oh no, I can't. And there's going to be a double bond there. I see it now. Yeah, and these are hard to interpret sometimes. But what I'm noticing here is this carbon doesn't have enough bonds to complete its noble gas configuration, and neither does this one. So there's got to be a double bond between them. So if there's a double bond between these 2 carbons, I could start with that. Then I've got 4 CH2s, so 1, 2, 3, 4. and then that fourth one is bonded to a CH3. So there's my bond line representation for that formula. And if I want to draw different rotational conformations, then I just rotate this bond. So instead of having it come down, I could have had it pointing up. So that's another slightly different rotational version of that structure. I don't have to just rotate this one methyl group or CH3 group up. I could also rotate here, and that would push these two carbons down at an angle. So there's another angle I can do like that. Right? So as long as they're all bent at roughly a 109-degree angle, the direction they're pointing in space isn't really that important right now. We'll talk more about that later. But you want to get used to seeing that in different with different angles is still being the same molecule. And then here finally the last quiz question, and just to verify the answers here, this carbon here is bonded to 3 CH3s, so that carbon is going to be bonded to 1, 2, 3 CH3s. It's also bonded to another carbon, which is bonded triply to a nitrogen, so that I won't have any extra hydrogens, right? There's no hydrogens shown on this carbon. The only way to make that the case is if there's a triple bond there. And when I count up all the valence electrons that would be here, it should match with that structure, so that confirms the structure should be correct, as well as the fact that there's no formal charge anywhere also makes it more reasonable. For this one, I've got my end carbon. It's got 2 chlorines. It's got 5 CH2s in a row. 1, 2, 3, 4, 5. And then it's bonded to a carbon that has 2 oxygens and this hydrogen. If I imagine the hydrogen on the carbon, then these oxygens would need enough electrons to complete their noble gas configuration, and they would be charged. That wouldn't be very stable. So that suggests to me that this last hydrogen is actually going to be on one of these oxygens. But then I notice that this carbon doesn't have any hydrogen shown on it. And so if I just leave it like this, which is often what students do, this would imply that there's a hydrogen here because there's only 3 bonds shown. But if there's no hydrogen in the formula, I can't have one there. So that prompts me to recognize there has to be a double bond there. And most people got that done nicely in the quiz. Well, that was a tricky one. Nice work. And then the last one, I've got the CH3. It's bonded to a CH. The CH is bonded to a bromine. This CH is also bonded to the next CH, and that's bonded to an NH2. Then it's also bonded to the next carbon, and that carbon is bonded to 3 different CH3 groups. 1, 2, 3. So there's that structure. Any questions about anything we talked about? So there aren't many bullet points here, but there's a lot of different ways these questions should be asked. So I highly recommend you do as much practice as you can. If you're not getting things correct when you're working on the practice problems here in the textbook, when you check your answers versus the solutions guide, please let me know. I'm happy to sit down with you and discuss some examples and try to explain them in more detail. Next Tuesday, we're going to continue in Chapter 2. So these videos and sections you should prepare. These will help you for the Day 4 quiz that will be due before class, before 1 p.m. on Tuesday. And then as you're studying for next week's exam, feel free to send me a message if you have any questions about anything. Oh, I forgot to check the, oh, that's, okay. I forgot to check the lecture text during lecture. Oh yeah, there's a lot of stuff in here. Geez, sorry about that. Yeah, people are answering questions. I'm sorry, for some reason I didn't think to look in here. My phone was off. Yeah, Amy's mentioning the mechanisms app. That's a good one as well. So I just want to mention that. This last slide here showing we're going to start talking about resonance. And once we do, there's some practice in the mechanism app that's due. That first assignment's due on September 9th, I believe. So if you haven't yet downloaded that, you want to do that soon so you're able to get that assignment in before the 9th. Oh, thank you for clarifying that already. You guys are way ahead of me. Jeez. I feel like a bum. All right, well, if you do have any other questions, I'm going to stick on for a little while, just in case anyone wants to speak up or type anything in now that I'm actually looking at the text thread. I will try to do that on the regular. I don't know why I forgot today, but apologize for that. So, I'll see some of you tonight. So, hope everybody has a great day.
I did have one question.
Sure.
The example you did that was C5H9ClO. The fact that there were an odd number of hydrogens, is that kind of what told you that one of them would be connected to a heteroatom?
Yeah, that does happen when there's a nitrogen in the molecule often. So I don't know if that's helpful to remember or not, but it's kind of something you could memorize. If there's a hydrogen, or if there's a nitrogen, if there's an odd number of nitrogens, usually just one, that often brings in an extra nitrogen or an extra hydrogen into the structure. So you end up with an odd number of hydrogens. If you have a structure with 0 nitrogen atoms, then it's really not very common for there to be an odd number of hydrogens. So that is kind of a red flag to help you kind of go through and make sure that you counted them correctly and that you are representing the correct number.
Okay, I was just wondering how you got to that so quickly, that hydrogen being on that heteroatom.
Yeah, it's also just experience and practice.
So is everything else.
Yeah, right, just like everything in life.
Alrighty, thank you.
You're welcome.